Our planet is a marvel of diverse climates. From scorching deserts to icy tundras, each region presents unique challenges and opportunities for those who dare to build. Architecture, at its core, is a response to these environmental conditions. It is the art and science of creating spaces that protect us from the elements while harmonizing with the natural world. For centuries, humans have instinctively understood this connection. We have crafted homes that provide shelter from the sun, wind, and rain. We have designed structures that maximize natural light and ventilation. This innate understanding of climate-responsive design is evident in traditional building practices across the globe. Think of the thick adobe walls of desert homes designed to absorb heat during the day and release it slowly at night. Consider the steeply pitched roofs of houses in snowy regions built to shed snow and prevent collapse. These examples highlight the ingenuity of our ancestors who recognized the importance of working with, not against, the forces of nature. Today, as we face the growing urgency of climate change, the need for climate-responsive architecture is more critical than ever. We must move beyond simply mitigating the negative impacts of our buildings and strive to create structures that actively contribute to a healthier and more sustainable future. The climate of a place is not just about the weather on a given day. It is a complex interplay of factors that profoundly influence the design, construction, and performance of buildings. Ignoring these factors can lead to uncomfortable, unhealthy, and unsustainable living spaces. Firstly, climate has a direct impact on thermal comfort. A well-designed building should provide a comfortable indoor temperature year-round, regardless of the weather outside. This means keeping the interiors cool in hot climates and warm in cold climates, without relying excessively on energy-consuming systems. Furthermore, climate heavily influences a building's energy efficiency. Buildings are responsible for a significant portion of global energy consumption, much of which is used for heating, cooling, and lighting. By designing structures that maximize natural light, passive heating, and natural ventilation, we can drastically reduce energy consumption and minimize our carbon footprint. Beyond energy, climate also affects the durability of building materials. The choice of materials should consider local weather patterns. For instance, using corrosion-resistant materials in humid coastal areas or opting for materials with high thermal insulation in regions with extreme temperatures can significantly extend the lifespan of a building. Moreover, the health and well-being of occupants are directly linked to the quality of the indoor environment, which in turn is influenced by climate. Proper ventilation, humidity control, and protection from extreme temperatures are crucial for maintaining good indoor air quality and preventing respiratory problems and other health issues. Lastly, climate-responsive architecture is fundamental to environmental responsibility. By reducing energy consumption, minimizing waste, and promoting the use of sustainable materials, we can lessen the environmental impact of our built environment and contribute to a more sustainable future. The Earth's surface is a tapestry woven with diverse geographical features. Each element, from latitude and altitude to topography and vegetation, plays a crucial role in shaping the local climate and consequently influencing architectural design. Latitude, the distance from the equator, dictates the intensity and duration of sunlight a location receives. Buildings located closer to the equator require designs that prioritize shading and ventilation to combat the intense heat. In contrast, structures in higher latitudes benefit from designs that maximize solar gain to compensate for the weaker sunlight. Altitude also plays a significant role. As we ascend to higher altitudes, the air becomes thinner, leading to lower atmospheric pressure and temperature. Buildings in mountainous regions often feature steeper roofs to facilitate snow shedding and thicker walls for insulation against the cold. Topography, the arrangement of natural and artificial physical features of an area, further influences local microclimates. Hills and valleys can create wind tunnels or pockets of stagnant air, impacting ventilation and temperature. Architects must carefully analyze these patterns to optimize building orientation and design. The presence or absence of vegetation also plays a vital role. Trees and plants act as natural air filters, provide shade, and help regulate temperature through evapotranspiration. Integrating vegetation into and around buildings can significantly improve their microclimate and reduce the urban heat island effect. Finally, the built environment itself influences the local climate. The density of buildings, the materials used in construction, and the presence of paved surfaces can all impact wind patterns, temperature, and air quality. Understanding these interactions is crucial for designing buildings that integrate harmoniously with their surroundings. Section 4. The Sun's Embrace, Solar Radiation and Design. The Sun, our nearest star, bathes the Earth in life-giving light and warmth. Understanding the dynamics of solar radiation is fundamental to designing buildings that harness this energy efficiently while mitigating its potential downsides. The amount of solar radiation received at a particular location depends on factors like latitude, time of year, and time of day. Buildings located in lower latitudes receive more direct sunlight throughout the year, while those in higher latitudes experience significant variations in sunlight intensity and duration with the changing seasons. Architects can optimize building design to maximize or minimize solar heat gain depending on the climate. In cooler climates, incorporating large south-facing windows can capture sunlight for passive heating during the winter months. Conversely, in hotter regions, strategically placed overhangs, awnings, and shading devices can block direct sunlight, reducing the need for air conditioning. The orientation of a building also plays a crucial role in managing solar gain. Aligning the building's long axis along the east-west direction allows for maximum exposure to the sun during the cooler morning and evening hours, while minimizing heat gain during the hottest part of the day. Furthermore, the choice of building materials can influence solar heat absorption and reflection. Light-colored surfaces reflect more sunlight, keeping the building cooler, while darker surfaces absorb more heat, which can be beneficial in colder climates. Understanding the intricacies of solar radiation allows architects to design buildings that are not only energy efficient, but also provide comfortable and healthy living spaces. Section 5. Temperature's Dance. Adapting to heat and cold. Temperature, a fundamental element of climate, plays a critical role in determining human comfort and influencing architectural design choices. Buildings should act as mediators between the external environment and the interior spaces, providing a comfortable temperature range throughout the year. In hot climates, the primary concern is mitigating heat gain and ensuring adequate ventilation. Traditional architectural styles in such regions often feature high ceilings, courtyards, and verandas to promote natural ventilation and create shaded outdoor spaces. Thick walls constructed from materials with high thermal mass, such as adobe or stone, can absorb heat during the day and release it slowly at night, moderating temperature fluctuations. Light-colored exterior finishes reflect sunlight, further reducing heat gain. Conversely, buildings in cold climates prioritize heat retention and minimizing heat loss. Compact designs with minimal surface area reduce exposure to the elements, while well-insulated walls and roofs prevent heat from escaping. Windows, while essential for natural light, can be significant sources of heat loss. Double or triple-paned windows with insulating gas fillings can significantly reduce heat transfer. Additionally, strategically placing windows to maximize solar gain during the winter months can contribute to passive heating. Understanding the nuances of temperature variations allows architects to employ passive design strategies that create comfortable and energy-efficient buildings, regardless of the climate.